Welcome to all on my channel Mathematics with Sachin Dixit. This is second lecture on dynamic programming. In previous lecture we make introduction to a dynamic programming and we solve one simple example on dynamic programming. In this lecture we discuss one more example, and from these two examples we point out some characteristics of dynamic programming and we discuss some terminologies in dynamic programming. In last lecture we discussed the solution of dynamic programming is based upon Bellman's principle of optimality, which is as follows. Here we just revise the this Bellman's principle of optimality. As an optimal policy has the property that whatever be the initial state, various conditions and initial decisions, the remaining decision must constitute an optimal policy with regard to state resulting from the first decision. Mathematically, this optimal policy can be written as Fnx is equals to optimum. In first lecture, here we have to write down maximum. Now here it is optimum. The more clear or more mathematically correct will be optimum, because this dynamic programming is used to find out the maximum value as well as minimum value also. Hence, to make clear the concept, here write optimum from onwards. Hence, Bellman's principle of optimality mathematically can be written as Fnx is equals to optimum over Dn belonging to set of all x on of R of Dn plus f of n minus 1 of t of x dn, where Fnx is equals to optimal return from an n stage process when initial state is x. R of dn is immediate return to decision dn. T of x dn is the transfer function which gives the resulting state, and curly brace x is the set of admissible decisions. In previous example, we take an previous lecture, we take an example to maximize the term. Now here we take the example on minimization. Divide the number 9 into 3 parts, x1, x2, x3, such that x1 square plus x2 square plus x3 square is minimum. Solution. Let the number 9 is divided into 3 parts, x1, x2, x3. Therefore, x1 plus x2 plus x3 is equals to 9. We have to minimize z is equals to x1 square plus x2 square plus x3 square. Here 3 variables. Therefore, here we have a decision variables x1, x2, x3. Therefore, the state variables are also 3. We denote it as s1, s2, s3, and define s3 is equals to x1 plus x2 plus x3 is equals to 9. S2 is equals to x1 plus x2. This can be written as s3 minus x3 by previous relation, and s1 is equals to x1, single variable, and this term can be written as s2 minus x2 from this previous relation. Now, next, by using Bellman's principle of optimality, we have f3 of s3 is equals to minimum over x1, x2, x3 of x1 square plus x2 square plus x3 square. That is, f3 of s3 is equals to minimum over x3 of x3 square plus f2 of s2, equation 1. Similarly, f2 of s2 is equals to minimum over x2 of x2 square plus f1 of s1. Equation 2. f1 of s1 is equals to minimum over x1 of x1 square. Equation number 3. From equation 3, we can write f1 of s1 is equals to x1 square. But x1 is nothing but s2 minus x2. Therefore, f1 of s1 is s2 minus x2 bracket square. Next, from equation 2, f2 of s2 is equals to minimum over x2 of x2 square plus f1 of s1. Now we put the value of this f1 of s1. We get f2 of s2 is equals to minimum over x2 of x2 square plus s2 minus x2 bracket square. To minimize x2 square plus s2 minus x2 bracket square, we use calculus as follows. Let z1 is equals to x2 square plus s2 minus x2 bracket square. For maximum or minimum of z1, dz1 by dx2 is equals to 0. We have to find out the first derivative of this function. That is d of dz1 of dx2 is equals to derivative of x2 square is 2x2 and derivative of x2 minus s2 bracket square is 2 times of s2 minus x2, and this s2 minus x2's derivative of s2 minus x2 is minus 1 equal to 0. Now we have to simplify this function. Multiply this minus 1 to this expression. We get 2x2 plus 2 minus 2s2 plus 2x2. This 2x2 plus 2x2 gives 4x2 minus 2s2 is equals to 0. Then 4s2 minus 2s2 is equals to 0 implies that x2 is equals to s2 upon 2. 2 gets cancelled, we get 2x2 minus s2, and that gives x2 is equals to s2 upon 2. Equation number 4. But s2 is equals to x1 plus x2. Put here, we get x2 is equals to x1 plus x2 divided by 2. Multiply this 2 to this side, we get 2x2 plus is equals to x1 plus x2, and that gives x1 is equals to x2. Equation number 5. This gives f2 of s2 is equals to minimum over x2 of x2 square plus s2 minus x2 bracket square is minimum when x2 is equals to s2 upon 2, and its value is given by f2 of s2 is equals to x2 square plus s2 minus x2 bracket square. Now we have to put this value of s2 by 2 in this expression. We get f2 of s2 is equals to s2 upon 2 bracket square plus s2 minus s2 upon 2 bracket square. s2 upon 2 bracket square gives s2 square upon 4. s2 minus s2 upon 2 gives s2 upon 2, and square of this term is again s2 square upon 4. s2 square upon 4 plus s2 square upon 4 gives 2 times of s2 square upon 4. This 2 and 1 2 on this 4 gets cancelled out, and we get f2 of s2 is equals to s2 square upon 2. Equation number 6. Next, from equation 1, f3 of s3 is equals to minimum over x3 of x3 square plus f2 of s2. Now we put this value of f2 of s2 here. We get f3 of s3 is equals to minimum over x3 of x3 square plus s2 square upon 2. But s2 is equals to s3 minus y3. We put that value in that expression. We get f3 of s3 is equals to minimum over x3 of x3 square plus s3 minus x3 bracket square divided by 2. Just simplify. For simplification, we take 1 by 2 common from this expression, and we get minimum over x3 is equals to 1 by 2 into 2x2 square plus s3 minus x3 bracket square. Again, to minimize 1 upon 2 into 2 times of x3 square plus s3 minus x3 bracket square, we use calculus as follows. Let z2 is equals to 1 by 2 into 2x3 square plus s3 minus x3 bracket square. For maximum or minimum of Z2, dz2 by dx3 is equals to 0. dz2 by dx3 is equals to 1 by 2 as it is, 2 as it is. Derivative of x3 square is 2x3 plus s3 minus x3 bracket square. Derivative of this function gives 2 times of s3 minus x3, and derivative of s3 minus x3 is minus 1. It is equals to 0. Now simplify this. For that, multiply this 1 by 2, this bracket. This 2 and this 2 gets cancelled, as well as this 2 and this 2 gets cancelled. This minus 1 multiplied by this plus sign, it gives minus sign. Therefore, dz2 by dx3 is equals to 2x3 minus of s3 minus x3 is equals to 0. Now multiply this minus sign to this bracket. We get 2x3 minus s3 plus x3. This plus x3 and this 2x3 gives 3x3 minus s3. Therefore, dz2 by dx3 is equals to 3x3 minus s3 is equals to 0. Then 3s3 minus s3 is equals to 0 implies that s3 is equals to 3x3 and x3 is equals to s3 upon 3. But s3 is equals to 9. Therefore, 9 divided by 3 gives 3. Therefore, x3 is equals to 3. Since x3 is equals to s3 upon 3, therefore 3x3 is equals to s3. But s3 is equals to x1 plus x2 plus x3. Therefore, 3x3 is equals to x1 plus x2 plus x3. This x3 and this x3 transfer on this side. We get 2x3 is equals to x1 plus x2. But from equation 5, x1 is equals to x2. Therefore, the above relation gives 2x3 is equals to x1 plus x2. That is 2x3 is equals to 2x1. x3 is equals to x1. Thus, x1 is equals to x2 and x3 is equals to x1. That is, x1 is equals to x2 is equals to x3. But x3 is equals to 3. Hence, x1 is equals to x2 is equals to x3 is equals to 3. This gives f3 of s3 is equals to minimum over x3 of 1 by 2 into 2x3 square plus s3 minus x3 bracket square is minimum when x3 is equals to s3 upon 3, that is x3 is equals to 3 and its value is given by. That means we have to put this x3 is equals to 3 in this expression. f3 of s3 is equals to minimum over x3 of 1 by 2 into 2x3 square plus s3 minus x3 bracket square. Put the value x3 is equals to 3 and s3 is equals to 9. We get f3 of s3 is equals to 1 by 2 into 3 square plus 9 minus 3 bracket square. 3 square is 9, 9 into 2 is 18. 9 minus 3 is equals to 6, 6 square is 36. 36 plus 18 is 54 and this 54 divided by 2 gives 27. Therefore, f3 of s3 is equals to 27. Hence, the optimal policy to minimize z is equals to x1 square plus x2 square plus x3 square subject to x1 plus x2 plus x3 is equals to 9. x1, x2, x3 all are positive greater than or is equals to 0 is x1 is equals to x2 is equals to x3 is equals to 3 and minimum value of z is equals to 27 is equals to 27. That completes the second example. First example is for maximization and second example we have to discuss it is for minimization. Now from these two equations we can point out some characteristics of dynamic programming. As first, the problem can be divided into stages with a policy decision required at each stage. Every stage consists of a number of states associated with it. The states are different possible conditions in which the system may find itself at that stage of problem. Decision at each stage converts the current state into the next state. The state of the system at a stage is described by a state variable. Given the current state, an optimal policy for the remaining stages is independent of the policy adopted in previous stages. The recursive relation is formulated with n stages. Using recursive equation approach, each time the solution procedure moves backward stage by stage for obtaining the optimal policy of each state for that particular stage till it attain optimal policy beginning at initial stage. Here from this there are two terminologies are included in this. One is stage and other is state. Now first we discuss these two terminologies in dynamic programming. First is stage. What is stage? The dynamic programming problem can be decomposed or divided into a sequence of smaller subproblems, and these smaller subproblems are called as stages. At each stage there are a number of decisions, alternatives, and decision made by selecting the most suitable alternative. The stages represent different time periods in the planning period. Next terminology is state. Each stage in dynamic programming problem is associated with a certain number of states. These states represents the various conditions of the decision process at a stage. The variables that specify the condition of the decision process or describe the status of the system at a particular stage are called as state variables. At any stage of decision making process, there could be a finite or infinite number of states. And one more point is return function. At each stage, a decision is made that can affect the state of the system at the next stage and help in arriving at the optimal solution at the current stage. Every decision that is made has its own worth or benefit associated and can be described in algebraic equation form called as return function. This return function depends upon the state variables as well as decision made at a particular stage. An optimal policy or a decision at a stage yields optimal return for a given value of the state variable. These are the three basic terminologies. Okay, in this lecture we discuss one other example, and from this we have to discuss some characteristics of the dynamic programming and three terminologies which are used in dynamic programming. In the next lecture we have to discuss a more general example on this dynamic programming. Okay. For a simple test on this lecture, the link is this. Type this link in your browser and check yourself. For this lecture, These are the reference books. Thank you.